Hello again. This is Roger Koch Barr for the Bioelectricity course. We're in week 7, segment number 8. This is a short segment, but that's okay because I've divided the segments, tried to divide the segments, according to what I think of as the importance of the topic, trying to keep different aspects of the topic together. In this topic, we're talking about the magnitude of the currents coming out of the fiber and going into the fiber. That's different. That's a different issue from the issue of where the sources are or what their sign is, which we've talked about a lot in the previous segments. So now we've said we've located some sources and some sinks in our fiber. How does one find the actual number value for that current source or current sink? Well, you get it from an equation, or you get it from a graph. So let's consider the two possibilities. First, let's suppose you get it from a graph. If you have a graph of the membrane current as a function of distance, you can basically just read it off the graph. That's the easy way to do it. The problem here is that that information is almost never available. Well, you can say, oh yes, but we just saw this in a graph that we had a couple slides back. How true? But that was a graph that was specially constructed from a computer simulation. It was not an experimental record. Interestingly, it is not possible experimentally to directly measure the membrane current. You can infer it from various other quantities, mostly voltages, but you cannot record it directly. So, taken as a whole, generally speaking, this plan does not work, although every now and then it does, and when it does, it's nice to take advantage of it. So we're back to our question. How does one find an actual number value for I0? And the answer is, you find it from the second derivative of the voltage trace, the second spatial derivative from the voltage trace. And you need some other values because you have I0 is equal to some constants out here, something in the numerator, something in the denominator, times the second derivative of Vm. Now, as you know from the earlier segments, the second derivative of Vm, this term, this is the change in slope. So plot out Vm, get out your ruler, figure it out. The question is, what do you do here and what do you do there? Well, you'll have to figure out exactly what the terms are. But I believe that up here in the top, there is a term that involves the radius A. And I believe that down in the bottom, there's a term that involves the quantity Ri. And I can tell you that for the computer simulations that have been done here, the value of the radius is 10 microns in most cases. You can see it at the top of the printout on the computer screen. And the value of Ri is 30 ohm centimeters in most cases. So usually that should work. If you think about it experimentally, it's a harder problem. But that's not to say an intractable problem. Experimentally, one has to figure out a way of measuring the fiber diameter from which the current arises. It can be done, but it can be tricky. Similarly, one has to figure out a way of measuring the resistivity of the solution inside the fiber. Again, that can be done, but it can be tricky. So I'd say from an experimental point of view, it's an achievable, solvable problem, but not an easy one to achieve. But it's important because once you get it, you know the actual magnitudes of the current sources, and the actual magnitudes of the current sources then control the waveforms that you see. So I chose this man for this segment because I think finding the magnitudes is an issue of now you see it, now you don't. So the eye patch that I believe has been attached to this face by some recent student, the eye patch sort of indicates that. With one eye you see it, with one eye you don't. That's very much the situation for the magnitude of the current sources. Thank you for watching. I'll see you again in the next segment.